So it just seems actually, it's, when I came to Ann Arbor, it kind of seemed like just a few years ago I was here. And I was standing here in front of Demos and my committee member, defending my dissertation. But actually it's not few, it's 21 years ago. Time really flies. And it feels just the same, except that Demos have few more friends here, right? And I'm again doing my dissertation defense or proposal, whatever. So what I'm going to be doing, but in all seriousness, it's actually really feel very humble to be here in this platform on this occasion, and grateful to the organizers for inviting. What I'm going to be talking about is the NFV, Network Function Virtualization. It's the business problems that it solves, and while solving those business problems, the many resource allocation optimization problem that it introduces. And then some of the implementation approaches that's like industry or the open source community is doing to address those problems. And actually lots of things that we discussed in the morning seems like how they are so applicable in this context. So I will try to finish a little bit early so that we have some time to discuss if there is any interest. So it's just a few years ago, this time really few years ago, not 25. So the industry was going through a lot of changes. Virtualization was becoming common, the ESXi, KVM, and the idea of virtualization was that over the hardware layer, you put a software layer, create kind of an abstraction so that you can run maybe multiple processes onto the same hardware, or you can move things around. So the virtualization really started becoming popular, especially in IT. And enterprises, they started using it, and it gave them a lot of cost saving. The Intel x86 processor started becoming faster and faster, not just in terms of the CPU, but also in terms of the I/O processing. And that is very critical for the network, right? The I/O processing is the one that counts. Can everyone hear me in the back? Okay. And then at the same time, Rackspace had a cloud platform. They were selling it to enterprise. So Rackspace and NASA joined together, and they open sourced their cloud platform, and it's called OpenStack. Once they open sourced it, they called it OpenStack. And its purpose was to orchestrate these virtual machines, as to say, because now you don't have real machines. You have the software layer and you have the abstraction. So you have the virtual machines, and how do you orchestrate the virtual machines and the applications running on top of it? So for that, they created this cloud orchestration and the open sourced it. And Intel also released, Intel of course wants to do faster and faster processing. They released a new technology called DPDK. What it does is that it, instead of using kernel space for the driver, it tries to use a user space. And that makes the things much faster because you have less interrupts. The network processing is way, way faster. And then the SDN, the software defined networking, it started becoming real. Some forms of it started getting deployed. So that was early 2010. So then at that time, while the enterprises IT was flourishing, over the top services were flourishing, and it seems like they are going to control the world, right? And operators were struggling. It was very difficult to be a network operator in that environment because that new services, because of this virtualization and all, these OTT players were launching new services like left and right. They will just drop the service, see if it works. If it works, it takes off, that's fine. Otherwise, they cancel it, they launch something new. And it was very easy for them to do it. Whereas the operators, they were stuck in their way of working. I wouldn't say stuck, but in some sense, because that's how their model was, right? So whenever they had to launch a new service, they have to get a new hardware. They have to and getting a hardware is a long process because you have to get the space, you have to get the power, you have to get the hardware. It can take 3 to 6 months. And then of course you have to test the applications, then you launch. So anytime you wanted to launch a new service, you need new hardware, and at the same time you have lots of unused hardware sitting in the network, because some of the services they thought will take off probably didn't take off, or some are obsolete, whatever. So you have lots of hardware, but it's not proprietary hardware because all the applications came in the box. Like basically you didn't buy the application, you bought a box and the box came with the application. And so they got together in 2012, 13 of them the main ones, and now of course the list is big, but in October 2012 the big names they got together and they figured out we need to do something about it. We need to change our model. And how can we leverage a virtualization to do something faster and be more agile? And the idea was to, okay, we want to use a standard server and storage. We don't want proprietary boxes because that makes life hard. You want to use, of course, you want to use efficient resource sharing utilization, because the virtualization does introduce about 10 to 20% penalty. So you lose the 10 to 20% capacity for the benefits that it offers, the flexibility. And of course, that it leads them to faster time to market, and it gives the it's the network operation is much more flexible, and it, hopefully, it kind of they can be as good as the life can be equally easy for them. And this is the picture I just did cut and paste from that white paper, and that actually exactly describe what we talked about, that they had all for this so many different, I just have few actually, there are a lot of applications, each one of them sitting in their own box, and you have to every time install at every site. And from there they wanted to evolve where they just have lots of high volume servers, they have Ethernet switches, standard storage, standard everything, and then on that they are going to put software layer, orchestrate, automate, run the new services. They can buy the software because now they don't have to from applications from anybody they want, they can throw it in. If it works, it's great. If it doesn't, they right. So they are also trying to be the same thing, right. So that was well and good. So they said, okay, why not just like the cloud, enterprise has evolved to cloud, let's us evolve to cloud, right. And this is again from the same white paper, that's what their vision, that you will have the network function virtualized, you will have SDN network, and you will have all the nice applications from anybody that you like, and you will put them together. There will be some overlap, and then you will have a telco cloud where you can run your applications. Of course, actually in hindsight this is a good picture, but the actually bubbles are overlapping. If now you think about it, the bubbles are overlapping more and more. So it's kind of becoming one unified approach. Okay. But the life was not so easy for them, and of course it's not going to be that easy for them, because the requirements from the enterprise cloud is very different than what the telco requires. What the enterprise have, they will have few large data centers. We always hear about Google, Facebook data centers, right? They are huge, they are remotely located, etc. But in telco, they have many small and distributed service centers close to. We talked, Ravi heard about in Rajiv's talk also, right? So they are called POPs, closer to the users. Then they have the enterprises generally have many VMs, and they are generally small, right? So even if one VM die, doesn't matter, and that's why it's commonly referred to as a cattle model. The idea is that if one of your cattle, something happens to it, you are not heartbroken, right? But the telco cloud is you have few and large VM, and if any one of them die, your network is in trouble. So you are really heartbroken, right? So they are referred to as PAT. So normally, like when you hear about enterprise versus telco, the battle is always between many times they refer to as cattle versus the PATS model, right? Just because of that. And of course, the user applications require large packet sizes. But when you are in the network, you have the small packet sizes, especially the voice traffic now goes just over packets, right. So, it is a very, very small packet, 64 bytes. So, your packet, how many packets you can process is becoming important, right. And you are only limited by CPU performance in the enterprise, but in telco your I/O becomes very important. That is why the release of Intel by DPDK driver and the faster I/O processing improvement became important in the telco world. And generally you can take a standard out of the box platform software for enterprise, but telco cloud can't just have software running on. There are certain situations where you need a specialized hardware. So, you have to be you can't be agnostic to the hardware. You have to know about your hardware, understand it in certain situations, especially if you have DSP and some kind of those kind of processing applications. And generate NG is good, software only switching is good for enterprise, but telco cloud it does not work. You need a lot more the speed, and then of course, the latency has to be small, but even the jitter is very important. Otherwise, the voice does not sound good, right. So, then you need spatial hardware acceleration techniques, and I would not go, but this SRIOV PCI pass through, basically it lets you pass through and access the directly hardware NIC instead of a virtual NIC in the virtualization model. So, with all that, so the people who met, the operators they met, they realized that it is not going to be just take the enterprise cloud and rename it telco cloud. That is not going to work for them. They have to do something little bit differently, little bit more in a standard way, because telcos is used to standard, right, because they want to be able to buy from somewhere, they have to interoperate. Like somebody from AT&T should be able to send or make a call to person in Verizon. So, they can't just work in isolation, right. So, they came up with this NFV reference architecture, and actually if any NFV paper you look, you pretty much you see this picture. So, they came up with like 4 or 5 years ago, but pretty standard, taken as a standard. So, in that try to use it. So, what is this? On the bottom we have the hardware, right. So, standard hardware software, the storage compute network. On top of it you put your virtualization layer, and then you get virtual compute, virtual storage, virtual network. Okay. And then on top of this the VNFs, that are the standard functions, not that's a standard function, but like the same functions that used to run before in a monolithic box. But of course, you can't just run it, they have to be redesigned to run in a virtualized environment. So, those applications you call it virtual network functions, they run on top of that virtualized infrastructure, and then you have the element management system to configure and manage these VNFs, these applications. So, this is your data plane. For the control plane you need the virtualized infrastructure manager, which has to manage all these virtual compute, virtual storage, virtual network, where they sit, how do they move, etc. You have the VNF manager that takes care of managing the VNFs, regarding like, okay, I want this VNF to suddenly get more processors, I want it to scale down, I want it to do whatever, I want it to live migrate, okay, because this compute is going to go down, I am going to take it out for service, I am going to move it to somewhere else. So, all those kind of things a VNF manager has to do the life cycle of the VNF. And then the orchestrator is the one super brain who decides, okay, who does where, what, like what needs to be done, which VNFs to be bring, what is happening, like kind of a more like a global kind of a person. And of course, it has to do security, authentication, anybody tries to log in, those kind of things. And then everybody has to, of course, have to some kind of a description should be there, right. You have to have some meta information so that you can tell everybody, okay, what is the property of this VNF, what is the requirement of this VNF, right. How much CPU wants, how much, like everything about it needs to be described. So, there is a lot of work being done as to how do you describe this, the whole everything like from VNF to other things. And then of course, this system has to work with the legacy operator OSS BSS systems or the new one, right. But you have to continue to work, you can't just have a completely new system for operations and business logic. So, that is the ETSI NFV architecture. Actually, any questions at this point? I can take it and then we can kind of changing the, no, okay. So, the next one. So, that is good. So, we learned about how the NFV architecture look like, how the life will be good when the operators get to deploy and everything working on it. But now, let us look at a real application. I just took one sample application as to how it works, what the operator has to deal with. Okay. So, here you have just the radio access, and I have made them as bubble because it itself, like I think Rajiv had talked about the details of these, some of these parts, that network itself is complex, and then there are gateway, and then beyond that, like just the voice, if you have to carry your voice, you have this complicated switching structure, because you cannot in 4G, you cannot take voice as circuit, you have to take voice as a packet. It doesn't have a, it cannot carry a circuit voice, it is only packet based, right. So, that comes the entire whole IMS infrastructure, where you have, I would not explain all the components, but like you have the call control agents, you have the media agents if you want to mix your media to do three-way calling, call waiting, those kind of things. You have the HSS, which is all the user information is kept. And then this part is very tricky and very important, because you have to also continue to work with 2G and 3G environment, right. You cannot not work, like a 3G user should still be able to call 4G. And actually often the operators are very constrained because of this backward compatibility, interoperability requirements. So, that puts a lot of burden on them too. And then you have other services, and then of course, you can have to take the call, you can take it to the PSTN depending on the number that is called, or you can take it to another voice over IP network, you can take it to 4G, wherever the call needs to go, right. And then they also have to meet all the regulatory environment like E911 and CALIA, etc. So, this is how the IMS looks like, and even this is architecture even with the boxes, even when you had the physical boxes, this is architecture, right. So, even with just physical boxes, it's complicated, right.
Where would the servers sit in that figure? They're on the
Which servers?
The servers and the storage that they were hoping.
Yeah, just one second. So, these are all like, these right now, just these applications are coming in as a boxes. Think of it as coming as a boxes, right. So, that was just the next slide. Okay. So, now you are trying to put this whole IMS in a virtualized infrastructure, right. So, now think of the complexity square, right, because you already had a very complex network even with physical to make everything working, and now you have to make it work on the virtualized platform where the things could be moving, and you have to make everything work, right. So, now these are the boxes, these are the standard, and you have the virtualization layer, and you have all the management VIM. And by the way, the VIM pretty much even the at&t decided to take OpenStack, the open source OpenStack. But the open source OpenStack does not meet all the requirements for an operator. So, actually there is a NFV working group in OpenStack to address operator requirements. So, when we try to do that, what do we get? You really have a, yeah. So, and why, like, today's morning discussion was very nice. Is it, do we really need to be centralized? Do we really need to be, like layered and all? So, there are certain situations where it's actually, I will get through that picture. I think I thought it was a picture, but probably it's the afterward. But anyway, so let's just go over the layers that it kind of comes in, right. So, now if you think about it, what's happening? You have physical resources, which are the computes, right? So, the memory, NIC, whatever. On top of it, you have a physical topology, how the compute 1 is connected to compute 2, how is it connected across the data center. So, you have physical topology sitting on top of it. On top of it, now you have a virtual topology, because you can create an overlay network, you can create all the virtual machines, and then on top of it you have the services, right, that the components, the functional components which saw in the previous thing like SBCs, CSCFs, right, the applications that were running in IMS. And then on top of it, really I do not care about personally that if how many components you use on the way. It is just that whenever I want to place a call, it needs to go on within the 200 milliseconds, otherwise I hang up and redial, right. So, the application, that is all the like end to end has to run, and it still gives the same performance. So, to manage all these layers that you are kind of having now, you have, of course, you have to do life cycle management, performance management, service chaining. Okay, after the service function, I need the next function, so on. And you have the constraint, the call still needs to go in 200 milliseconds. You have your policies, you have your orchestration. So, you see that this kind of side is also becoming more and more complicated. And to just not just that, there are situations, you have layers within the each layer. Like if you look at a typical data center, that is how a typical data center looks like. So, you have the physical servers, right, the blades probably, and then on them the virtual machines are running. Then you have top of the rack switches, then you have the the end of the row network switches, then you have the spine, they generally call leaf and spine architecture, then you have the spine, then you have the gateway and so on, right. And to manage it, you have sometimes this. So, these are also SDN controller, but there has to be a hierarchy, because you are kind of managing sometimes within a row, within a rack, and then within data centers, because these two SDN controllers might be in two data centers. And then you have this VIM, which is a virtualized infrastructure manager, to manage your compute and your everything. So, there is like it's just the way network is designed and just the way things are, it does start becoming a layered architecture naturally. And this is just to summarize we actually already discussed most of them. So, what does an NFV needs to do? It needs to orchestrate, onboard the new VNFs, the network functions. It has to do globally resource management, authorization. The VNF has to do life cycle management that we talked about, has to do configuration, event reporting. The VIM has to take care of the infrastructure, the virtualized infrastructure. The service performance still need to be met. And then you have a lot of operational issues, like you have to minimize the power consumption. We had a talk in the morning on that. You have to adapt to traffic conditions, especially like you are expecting it during busy hour or certain game, you have to take care of that. You have to have network to be highly available, because if you are not, you get penalized, because telecom is still a semi-regulated industry. And of course, then there are lots of other security, coexistence, you have to upgrade, etc. So, there are a lot of like operational challenges on that. And you can't really do everything centralized, because there could be admin boundaries where you can't like these again I took the picture from an ETSI report on how they expect to use the SDN, and they had 3 use cases, and I just put them side by side to kind of emphasize that there are options that sometimes you do because of resource utilization, and sometimes you have to do because that is how the admin boundaries are, or because of so many reasons which are not necessarily just technical. So, like in this case you have one WAN controller, in this case you can have because when the two data sites are trying to talk to each other, you have the wide area network, but you have to present a different abstraction to each of them, because probably it belongs to some different operator. These are operator A, operator B, this is operator C. So, you really can't have a single controller, even though service is spanning, has to go, the call has to go through all this, right. I am calling from AT&T to Verizon, it is going through all of the, just an example, from basically one network to another, and it has to go through the WAN link, which is probably owned by somebody else, etc. So, and then you can give each client direct access, but probably do not prefer because of security reasons. Even the your resource allocation policy might say, oh, this is the most optimal way to do. So, there are situations where we have to go to the hierarchical and distributed models, and you can't really share all the information because of multiple reasons. Okay. So, that is why it does lead itself to a hierarchical distributed resource allocation, where your objective is to optimize resource allocation at each layer, and the environment is fast changing, and you need to respond in real time. You cannot take delay because it is a network, we are all used to like instant response, right, instant reaction to our buttons whenever we press on our computer, cell phone. And of course, it is a distributed information, it is a stochastic environment, things are changing dynamic, new calls are coming, some calls are leaving and messages are going. So, how do we approach this kind of thing in a little bit more formal way? So, the one approach, and this is not the only approach, this is one approach that I have been thinking about is, okay, you have to understand application requirement. You have to first understand what your application requirement, and there might be other ways. So, just do not, this is just one suggestion. You have to understand your VNF, you have to know your infrastructure, and you have to know your infrastructure in detail. And then you formalize your scheduling problem, accounting for, you have to translate the application requirement to the VNF requirement, to the service function chain requirement, and how exactly you want to do, and how do you efficiently want to place your VNF into physical infrastructure, right. So, there are always you always have requirements that are coming from different constraints. So, what does it mean to understand application in terms of VNFs? Of course, the first and foremost requirement, it should be that user experience should be comparable, it should be at least as good if not better to traditional networks. Your call cannot take longer just because we are in virtual networks. And then decomposition of monolithic applications. Before, like you used to have one, like I showed you the IMS picture, right, but before IMS, when we had to have circuit switch voice, it was one big box, mobile switching centers, right. They will carry your voice, they will switch the voice, and then from there we went to a little bit distributed, where you have a call agent, you have media, you distributed them, you broke them into different things. So, you can buy it from different vendors if you need to, and also you can scale them independently, right. So, you kind of breaking it up, but the problem is that while the like enterprise applications, like some big video service provider, I would not want to name them, they have basically made their services called microservices. That their services very, very small, they just come and go, fast come and go in enterprise environment, but that works for them. When you try to do the same thing in a NFV environment, even though people do talk about, oh, we want to go to microservices, it does not really work at times. Because when I talk to the people who are really deploying the services, who are making the network work, they are like, yes, I can broke the services, but we do not want to because it increases the delay between the call setup time. So, there is always a trade off that in theory it looks like, yes, you want to decompose it into very, very small things, but probably not. So, what is the fine line? That is an open problem, where exactly you should, it may depends on the application. And then how do you place and change this virtual function, like all data same data center or different places, and how does the network services VNF and their relationship, how should you give the requirement of one to the other, like how do you describe a VNF? What exactly parameters it should include? How do you describe an NSF? How do you describe the relationship that this VNF depends on that VNF? That if I want to provide this call end to end, of course, I need my proxy call servers to be before I go to the serving call servers, and then I want the router to tell me where the route needs to go. So, I need that order, right? I need that service function chaining. So, we need to be able to describe all that, take into account like how much to break. And if you kind of go down a deep under that, it is possible to like even break each VNF into multiple smaller VNFs, and you still have to do, and it is running on that your hardware with a virtualization layer, and your hardware has a different kind of connectivity normally called an underlay network. On top of it you have an overlay network, and you just have things kind of, the mapping needs to be managed. So, that was understanding application. Now, you need to understand your VNFs. The VNFs are of course getting complex, they kind of require lot and lot things. They want to, if they break, they want to be self-healing. I have more load coming in, can I scale that application just like that, throw it more resources and make it bigger, and how does it depend on the external network. So, you really have to understand what is your VNF requirements are. How do you characterize your VNF, right? It depends, because the performance you get from your VNF may depend on the operating condition that you are operating in, right? And it can change depending on what kind of hardware you are running itself. So, what is the kind of measurement matrix that you should collect, right? There is always, you can collect more and more, but there is a cost to collection, whatever is small or big, and you have to understand your data. You can collect lot of data, but then there are problems. You have lots of data, but you do not know what to do with the data, right? You have to understand your data, and you have to learn to dynamically characterize your VNF. And I feel the machine learning is kind of is a nice technique just now ready that we can apply it to understand our VNF into this kind of environment. So, when I was doing my dissertation, and I think we did like all Gittins index, and it is a very nice problem, and Gittins index, but when I went to industry, always how do I apply it, how do I compute the Gittins index, right? And I feel now with machine learning, we are now will be able to do it. Finally we are at the breakthrough point where all that theory we have, which is such a very nice theory, will finally be able to apply it. And this is just like one attempt to characterize the performance and to emphasize that how. So, this is one application. It was actually it is an open source project again, and they have taken just one part of that IMS CSCF, and they have broken up into multiple VNFs, and they have interesting names on it. But the main important point is that depending on what kind of configuration you run in, you get different performance out of it. And you have 3 ones, you get the best of performance when of course they are all large, but if you have to throw more CPUs, like here everybody is medium versus here there is one person is large and one person and 2 are medium, and you did not really gain much, right? In fact, you lost something. So, you have to kind of understand that is it throwing more CPUs really going to help me in my case. So, this is weight run test in the lab, but in reality you can't really understand in all the dynamic environments. So, you have to do dynamic learning, machine learning on the spot, right? I do not have so these are basically, I have really open problems, I do not have any solutions, because I think everyone here is smarter than me here, and you will probably come with a better solution. So, that was like how do you get this thing. And then of course, you have to know your infrastructure in detail, really detailed. The more detail you can know, the better. You have to know how many vCPUs, oh sorry, yeah. So, you know how many, how do you, basically even the structure of CPU with the speed and processing you need starts getting important as to how your processors are located. Is this processor closer to the memory that you are accessing? It starts getting important, like it's called non-unified memory access support, etc. So, you have to understand the capabilities of each of your compute. You have to understand how fast your NIC capabilities they are, what kind of features they support, what's your network layout, what's the storage, you know how is the connectivity. So, know your infrastructure in detail, because your VNF performance depends whatever said and done on the hardware it is running, even with the virtualization abstraction. And this is again some kind of results to show that if you run the same VNF on the different server configuration, you get different performance, right? And the different VNFs can give you different performance, and depending on what kind of techniques you are using. So, now that once we understand applications, we understand VNFs, we understand infrastructure, how do you manage all this mapping of one to the other to meet the application requirement efficiently, right? So, again the approach would be, okay, you formalize the options at each layer, like application, how much I should decompose and how should I decompose, where should I decompose, how many VNFs and what is the forwarding graph among them. For the VNFs, scale up or scale out, you might have heard this term quite a lot. So, scale up is like throwing more CPUs to the same processor, same application. Scale out is creating multiple instances of the same application, right? And depending on the application type, one might be better than the other. Because if you are IO bound, no point in doing scale up, probably it is better to do scale out. Determine the way it scales, watch for noisy neighbors, because now you are sharing the infrastructure. So, your other processors that are running on the same infrastructure will also might just be competing for the same thing. How do you want to auto scale? The moment the traffic to me is increasing, can I auto scale? Can I auto migrate to a bigger node if I need to? Things like that, right? Understand your compute, understand your network, and we have to realize that decision that we make at each of these layers affects the performance of the other, right? So, it's you have to understand each layer, and then you do want to kind of treat each of them individually, otherwise the problem gets very complex, but at the same time somewhere some kind of abstraction is needed so that you can pass. I think we had a talk on that today, right, in the how to distribute, very interesting that where to do that. And then if you want to, again what is a kind of same thing, you know, keep detailed inventory, you have to be contextual, because whatever the right thing to do may not exactly be the same depending on the context, depending on what else is happening in the network and what else I am expecting it to happen in the network, right. And it needs to be dynamic with fast response time. So, there is this is kind of little diagram, but there is another idea that has also industry is working on, is that probably academics too, is that it is an intent driven framework, because the system is so complex now. Now, if I want to launch a service, can't really go and understand and tell, hey, open this port, put this thing here, open that, it is just too complex for a human to work through it end to end. So, the idea is getting onto around intent driven framework, that I just say this is what I want and then network delivers it. It is like I have a robot and I just tell the robot, get me a glass of water, but I do not have to exactly tell him every time you have to walk this way, you have to walk that way, then open the tap, you know, I do not have to give the instruction, just give what I want. But then the problem it considers that suppose I have two robots, one I want to bring food and one want to water, they are both going to the kitchen, they should not collide, right, or try to open the fridge at the same time. So, you have to take care of when you have this multiple things, that there is there is a mechanism to resolve conflicts, because when you say intent and you have different policies, you have policies at each layer, there should be a way to resolve the conflict among them. And you have to take care of all the constraints that is coming up. Any questions at this point? No, okay, go on to the next. So, so far like I know like kind of the problem and all, and then I am going to talk a little bit about the implementation approaches, that what unfortunately my knowledge of academics is not up to par. So, I would not be able to do a very good justice to describe what the work has been done in academics, but I will try to just describe how at least industry is trying to solve this. So, basically of course, this does the ETSI architecture that we talked about, and then lot of open source. Of course, industry proprietary ways are also there, but I thought open source is more interest to academics because they can directly contribute if needed, and there is the code is available, easy to work with. So, they took the architecture, and there is an industry consortium called NFV, which basically requires, okay, the ETSI architecture is nice, it is nice and abstract, a nice way of thinking about it, but how do I translate into the different things that are available. So, there are like different things available, open which from different foundations, and there are different projects that are going on. So, they try to put them together and see, can I make a working system based on just the open source. And I will just kind of give an example of OpenStack architecture. Again, it's a complex, it's huge software. Like I think there are so many people, anybody can contribute, because that's the idea of the OpenStack, right? Open source, anybody can contribute. So, and they have a conference every 6 months, and they do a new release. So, they have multiple sub projects within the OpenStack. So, basically this is what we are trying to launch, we are trying to launch a VM. So, then they have a interface, user interface, they come, user gives a command, okay, I want to launch a VM. Now, it wants to launch a VM, of course, there has to be some authentication mechanism. So, I took this picture directly from OpenStack, is that okay, you took it authentication, now the authentication happens, and I go to the Nova. Nova is the one who manages all the compute resources, and I'll say I want to launch a virtual machine. So, Nova says okay, fine, but I have to make sure whatever credentials you are giving are right, verifies it. Then the Nova has two parts actually, and the one part that runs in the controller, and of course, you have to have something running on each compute. Oh fine, okay, I will go fast. So, now you have to have something running on the VMs on the hardware, so that it talks to the Nova compute and in that part and say okay, give me some resources, figure out where I want to place, and then ask the neutron, give me the network, gets the image, and you basically feed it, and then you launch the VM. The purpose was just to show that there is a whole process, and it's kind of a complex process. And then the scheduler actually is very simple in that, like okay, it's very complicated, but Nova filter scheduler is very simple. It just looks at the host, available host, you want this, okay, just give me a high level requirement what you want, I cancel out which host which won't meet your requirements, I do some kind weighing, and I just pick up one and I give it to you. So, it is very simple, it is very fast, but of course, not optimal, right, it does not take care of that. So, it's there are other projects that are kind of going on to make the scheduler faster and faster. If here there is interest in following up, of course, I can talk offline about some of them that I know, but most of them are available. You can do this thing and this such. There is a new open source project called Watcher. It is of particular interest. It is kind of trying to bring more intelligence to all the resource allocation and all these issues. They collect the matrices, determines like this is a complex, the event processing kind of thing, figure out what information to keep, what information to throw away, stores it up, uses machine learning to figure out where you want to decision engine, where you want to place, there is all the database and plugin basically, and then it tells Nova what it should do. kind of, so trying to bring more intelligence into the architecture. And this is again some list of open source projects. It might be of interest to look into, regarding policy based intent composition, how to do it. And there are as with anything open source, there are multiple open source projects that are going on, sometimes trying to do the same thing, but different open source communities. So this is kind of a chart to help you through if you are interested, where to look for what. So there's a resource reservation is kind of a big thing, that if somebody knows I'm going to have a football game here, they want to reserve the resources, ahead of time, because I'm expecting a lot of things. So there are two people who are working on it and collaborating, some kind of thing. And this is just to kind of to end with it, just there of course all the big telecom operators are working on it. So this is not I'm just took 2 examples, not for any reason, just and it's available on internet. You can read their white paper. They kind of taking the at&t and they are saying how do they want to implement it. So at&t has some things, not exactly how to implement, but they kind of give implement and more discuss more of the issues into the what come when you are trying to do it. at&t has also done something very good, and they are also using machine learning. This DCA is all machine learning component to learn about that and sophisticated scheduling. They are kind of, they are both architecture and initial deployment phases. So they are kind of, if you are interested, it's kind of interesting to look around. And just to summarize, it's of course application and hierarchical distributed control becomes a necessity. And actually, as I kind of look into the problem, it's kind of realized that even though I am not working on it on day to day, what things I learned long ago, I still remember it and I can apply that. I can think through these problems in a little bit more systematic way. And with that, happy birthday, Demos, and thank you for teaching us what I could still remember. So thank you so much.
Now, one special case of this is when X and W are independent random variables. This is a more sort of a traditional formulation, U0, U1.